Hello, welcome to this week's tutorial on classification. Um, your classification is one of the algorithm that comes under the umbrella of supervised learning, right? Which basically distributes your data set into classes, right? The aim is to learn a classifier that usually maps a function f from an input data point to one set of discrete output classes, right? So it maps your data points to discrete output classes. These are basically based on many rules. If those are basically if then else. So let's take a linear classifier in two dimensions, right? So a linear, if you're talking about a linear classifier in two dimensions, it will be made up of x and y axis, right? Let's say we have the data points distributed right. So your classifier will basically distribute these two sets of data points into two different classes by building a decision boundary between them, right? So it builds a decision boundary which has a weight vector that is perpendicular to the decision boundary. You have x0, x1 and x2, different xi's, which point in the direction of your decision boundary, and you have a weight vector which is parallel perpendicular to the decision boundary. In particular, you have one x0 which is in the same line as w, right? So this line can be defined by w xi is equals to t, right? Where this is the dot product, right? And t is a decision threshold, right? So as you can see, x and w point in the same direction, therefore cos theta will become 1. Therefore their dot product is nothing but a product of their vectors, the length of their vectors, right? So now let's talk about how your classifiers are applied in real life, right? So let's take an example of spam filtering, right? So in spam filtering, all your emails gets divided into two classes that are spam and ham, right? You must have seen a spam folder in your Gmail account that basically works on the concept of more or less of this spam filtering. So what it says is, right, you have emails coming in, right? These emails go through a specified test called spam assassin tests, right? What they do is these tests convert text of each email into data points. So what your spam assassin tests do is they convert text to data points, right? You can use various concepts like bagging uh, to convert text into data points. Now this data is then fed into a linear classifier, right? Which has weights associated with them. So this linear classifier, on the basis of these weights, is able to classify an email as spam or ham, right? Now, how do we determine these weights? These weights are learned along the way, right? When the data is provided to it. So you input a training data, right? You learn the weights, you provide these weights to your linear classifier, and you ask the classifier to classify it, right? Okay, so this is how your spam filtering works. Now, this part where your classifier has to classify your email as spam or ham is called as the task, right? So tasks are addressed by the models, right? And this part of learning the weights and providing these weights to the linear classifier is called the learning problem, right? The learning problem are solved by learning algorithms that produce the models, all right? So machine learning is concerned with using the right features to build the right models that achieve the right tasks. So basically the models in machine learning provide the diversity to it, whereas the tasks and features, right? So the task is to classify and the features are based on the data points, provide the unity to machine learning, right? That brings us to the topic of linear classifier. All right, so that brings us to the next topic of linear classifier. Right. So in this, we are talking about a two-dimensional linear classifier. Let's say we have a set of data points which consists of points of two classes. Let's call them positives and negatives. Right. So the basic linear classifier will construct a decision boundary by halfway intersecting the line between the positive and the negative center of masses. So what I mean by positive and negative center of masses is, so let's say this is a whole class. We'll consider this as one unit and we'll calculate its center of mass. Let's say it lies somewhere here, right? And similarly, for the other class, for the negative class, we find the center of mass and we mark it, right? So the basic linear classifier will try to basic linear classifier will construct a decision boundary by halfway intersecting the line connecting the center of masses, right? This is not exactly halfway. All right, so let's say the center of mass, this is P, this is N, right? So this point would be what? This would be P plus N by 2, right? And as W passes through P, this line W is equals to P minus N, right? And the point is P plus N by 2, right? So now our decision boundary was described by the equation, right? And we have the point P plus N by 2 lying on the line, right? Where W is equals to P minus N. And this is called the separating hyperplane. So placing the value of W and replacing the value of X, we get P minus N into X is equals to T. P minus N multiplied by P plus N by 2 is equals to T. Therefore, our T results in right. Now, if we are to consider the length of the positive and negative center masses, right, what we need to calculate is this is equals to length of P. This is equals to length of vector N, and this would have been equals to, right, 2, right? This is because let's say if our P is denoted by x1 comma y1, therefore length of P would be equals to root of x1 square plus y1 square. Similarly, if this is x2 and y2, the length of N would be equals to root of x2 square plus y2 square, right? So now that brings us to a couple of definitions. That says what is deduction? Deduction is basically deriving specific consequences from general theory. Whereas induction means deriving general theory from specific observations, right? Deriving general theory from specific observations, right? So these are way two very different terms, right? So now that brings us to inductive learning hypothesis. Inductive learning hypothesis. Inductive learning hypothesis is any hypothesis found to approximate the target function or the true function well over a specific large set of training data will also be able to approximate the target function over other unobserved data, right? Let's say you have this state space, right? And inductive learning hypothesis says that if a function works well on one data, right, it will be able to work on the unobserved data as well. Let's say this is observed, this is unobserved. Therefore, we are deriving general theory from specific observations. We observe this and we generalize that this function will fit over this unobserved data really well too, right? So that brings us to our next topic, cross-validation, right? So whenever you have a data set, that data set is divided into two parts, right? A data set is divided into two parts. One is the training set and one is the test set. So generally, as a good practice, like if you have a data set, you generally divide it into 90 and 10, where this 10% of data is untouched till we're sure of the model that we have built, the hyperparameters that we have calculated, and like we have the final working model, and we use this test data to test its performance, right? That is where the testing accuracy and all comes in, right? But now we are faced with a problem that each algorithm has many different parameters or hyperparameters that are needed to be tuned, right? Because tuning, like you can achieve a certain level of or a certain accuracy with a model, but if you want to break through or go over that, you need to tune your hyperparameters for any algorithm, right? So these certain parameters, for the tuning of these certain parameters, what we do is we use a validation set or development set, right? So how this development set works is, right, like initially we used to have a training set and a test set. This is initially, right? But when we wanted to tune your hyperparameters, we started using the validation set. So validation set is basically a part of your train set only, and your test set is still kept separate, right? This is basically your one-fold validation, right? Where what you do is, like, if you, this consists of your 100% of your data set, test set is 10%, and your training set is 90%. So of that 90%, the further 10% or 30 or 20, like that depends on you, gets divided into a validation set. So that makes us left with 80% of training set. This 10% of validation set is then used to calculate the hyperparameters or the parameters or tune them, right? So now that brings us to the concept of k-fold cross validation, right? So if let's say, let's talk about threefold cross validation, right? In threefold cross validation, you have a training set, right? This training set gets divided into a validation set. This is valid and this is training. But if you're talking about a threefold validation, in threefold validation, what occurs is your same training set gets divided three times, right? Where this is train, valid, train, So if you're talking about a k-fold cross validation, that means your training set will be divided, or you're folded over and over k times to find different training and validation set, right? I'll explain what this is. This would be validation and this would be training, and your test set remains the same, right? This is done so because like if you have like over a million lines of data, right, and you have variety in your data, so let's say if you divide, just if you use one fold validation, you won't be able to account for all the variety in the data, right? You'll just be able to take this much part for the validation or development set, or the middle part or the front part for the validation set. So in order to accommodate the variety and the different values, because all of these values play a major role in deciding the weights or your parameters of your algorithm. So the variety of data is needed to be accommodated in our algorithm. Therefore, we use threefold or k-fold cross validation. This is also really helpful when you have a small data set. Let's say if you have a data set of 500 lines or 1000 lines, so this will multiply your data set, right? Because every time if you keep sampling a different part of the data set, you'll get different inputs every time. Hence it increases the type of testing or the training that you do, right? So that brings us to another really important topic, that is the contingency table. Right. So whenever you use a classifier, right, so that classifier will have an actual class that it has to match, and it has a predicted class, right, that it outputs, or the output of the classifier. Let's say we're talking about just yes and no, right? So the if you're talking about spam, so let's say the actual classes are spam and ham, and the predicted classes will also be spam and ham, right? So this is two class classification. So in order, like if your algorithm gets an input that has an actual class as yes, and your algorithm predicts the output for that specific input as yes, that means it's a true positive, right? Whereas if your actual class is yes and your predicted class is no, that means it has falsely identified that sample as a negative, therefore false negative, right? Now if your actual class is no while the algorithm deducted it as yes, that means it has falsely sampled that label, that class or that data set data point as positive, therefore this becomes false positives. And the final one would be, if you have negative class label and your predicted label is also negative, that means it has truly classified it as negative, therefore it becomes true negative, right? The use of this table is very diverse, because you can calculate precision, recall, your accuracy, all all of these can be calculated on the basis of this table. All of these terms will be tackled in the coming lectures that I'll take. All I can say is, okay, if anyone asks how many samples have your algorithm classified correctly, that would be your true positives plus your true negatives, right? And similarly, because it's yes and it is predicted as yes, it's no and your algorithm has predicted it as no. Therefore, these two consist the correctly classified labels, while these two form your incorrectly classified labels. Right. So now that brings us to accuracy. All right. Let's say you have a data point X and an associated label CX with it. Right. And you have a linear classifier or a classifying algorithm that predicts when the input X is provided, it outputs a class value C hat X for it. Right. This is the predicted label, while CFX is actual label or class. Right. So accuracy in this term is the total number of samples that we take. Right. We use an indicator function which is basically which outputs 1 if your actual label matches your predicted label, if C hat X is equals to C of X, and 0 if not. Right. So using a simple indicator function, we can calculate the accuracy of it. Right. That means it will be 1 for all true positives or true negatives, while it will be 0 for all false positives or false negatives. So if you see, if it's 1 for all true positive and true negatives, then the only time 1 will be added is if C hat of X is equals to C of X. That brings us to T that I told, the total number of correctly classified samples upon total number of samples. That gives you your accuracy. Right. Now let's talk about distances. Right. Okay. So let's talk about distances. If X is a real number, right, then Minkowski distance of order p greater than 0, let's say p be a parameter. Okay, so you see the distance from x between x and y is yj to the power p 1 by p. Right. That gives us x minus y p. This is the notation where p is the parameter. Right. Where if anything is noted like this, this means to the power 1 by p, where j goes from the data points. This is also called p norm or LP norm of vector z. Right. So what if p is equals to 2? If p is equals to 2, it is called Euclidean distance. It is called a Euclidean distance, where x and y, this 2 means that is 2 norm. Right. This gives us sigma from 1 to d j minus yj square and under root of it. That means xj minus x minus y, L2 norm, right? And if we want to represent this in matrix notification, this would be root of x minus y transpose into x minus y, right? Which is also equals to root of sigma of xj minus yj square, where j goes from 1 to d, right? So this was basically your Euclidean distance. So we covered up. So your one norm distance is called normal Manhattan distance, or your city block distance, right? This is a straightforward xj minus yj, right? So this is called your Manhattan city block distance. Now what if your p is equals to infinity? So this is equals to j1 to d, right? Now here we use limits, right? Because we have the power of infinity. So that becomes okay, show it to you. Okay. So if we have this, then limit if p tends to infinity and sigma of xj minus yj to the power p 1 by p, we get max of xj minus yj. Therefore, for p is equals to infinity, also called Chebyshev's distance, is equals to max of xj minus yj. Then another common term that you might hear is zero norm, right? Zero norm is basically it counts the number of non-zero elements in a vector. The corresponding distance that counts the number of positions in which x and y differ. That is it, right? So your distance zero or zero norm distance would become just your indicator function, where it's equals to 1 when both the bits in your vectors x and y are same, and 0 if otherwise, right? So that covers your zero norm distance. Um Then you have your Hamming distance and Levenshtein distance. Levenshtein distance is basically between words. So there's a concept called Damirov-Levenshtein distance, DL distance, that calculates the difference between words. Like if I take the example of bat and cat. So the DL distance between bat and cat is of 1, because it compares all the positions. So it sees B and C have different elements here, and the difference between B and C is equals to 1, right? So DL distance helps us in spelling correction, and it can help us in bagging the model. So okay, Hamming distance, it is double M. Hamming distance, if x and y are bit strings, right? If x and y are bit strings, then distance is the number of bits to be flipped in order to convert x into y, right? So if you have 1 0 1 0 1 1 1 as, let's say, x, and y is 1 0 0 0 0 0 1, so you need to flip 1 2 and 3 bits. This is y basically. So you need to flip 3 bits to convert x to y. Therefore Hamming distance would become 3. right? So now that brings us to the concept of K-nearest neighbors. Okay, so that brings us to our next topic, that is nearest neighbors, right? So the nearest neighbors algorithm works on the concept of similarity or distance between your data points, right? It is basically a simple idea that instances close by, or the data points close by on the plane, are should be classified similarly, or are of same type. Like if you have crosses and zeros, right, and you have a new data point that is a cross, it will obviously be close by to its similar one. Therefore, it should be classified similarly, right? So this is a type of lazy learning. This is lazy learning because you need to present the algorithm with the whole of the data set in order to make a prediction, right? This also forms the base of unsupervised learning. In unsupervised, specifically clustering, that we'll tackle in the coming lectures. All right, so you just need to follow a few steps in order to form your nearest neighbor algorithm, right? The first step would be that store all your training examples into a list, basically. So number one would be store training examples that are of the form in a list, right? So if you have just the nearest neighbor, where you just consider one single neighbor, therefore given if you have a new training instance xq, okay, you locate the nearest neighbor or the nearest training example xn, right? Locate xn that is nearest to xq, right? And then estimate f hat xq, that means the output, as f of xn. That is basically x of q has been classified similar to xn because xn is the closest neighbor to it, right? But what if you consider k closest neighbors, right? If you're considering k closest neighbors, that is knn, k nearest neighbors, so you have given xq, right, as a new instance. You take a vote among the k nearest neighbors, k nearest neighbors, if your target value is if your target label is discrete value, right? Discrete valued as in yes or no, right? So let's say if you have to take 5 neighbors for xq, you find 5 points that are closest to xq, right? Let's say in these 5 points, those are x1, x2, x3, x4 and x5, right? 3 of them are yes and 2 of them are no. So taking a vote, that means f hat xq would be equals to yes. The majority is yes here, right? But what if your target function or your target label is continuous valued or real valued? So in that case, if real valued, we take the mean of all the f's. So if real valued target function, we take the mean of all the f of x, right? We are considering k neighbors, so till goes till k. You find the xi's for all the k neighbors and you take the mean of it to determine the output, right? So this algorithm has basically two parts. The first part is the training algorithm. The training algorithm basically lists all your x and labels into a training example list, right? This forms your first part, that is your training algo. The second is classification algo, right? In classification algorithm, if you have a given given a query instance xq, that is a new sample that is introduced to the classifier, and we want this xq to be classified, right? To be classified, what you do is, um, we find out x1 till xk, the nearest neighbors to this value xq from this list, right? We find the value of x1 till xk that are nearest to xq, and then what you return is f hat xq equals to max sigma of delta v comma xi, where I goes from 1 to k, right? Where delta is again an indicator function which will output 1 if v is equals to f of xi and 0 if not, right? Now that completes your two steps of your nearest neighbor algorithm. Now let x be described as a feature vector. Obviously your any data point x will be made up of different features, so let it be described by a feature vector that is given as a1x, a2x till amx. That means it has m features, right? Where a r of x is the rth feature or attribute of x, right? Now if you want to find the distance between two instances or two examples instances xi and xj, so if we represent this distance in terms of features or the feature vectors, we will get d between xi and xj as root over sigma of I from 1 to m, or let's take it as r from 1 to m, a of r x I minus a of r xj squared. So you take the difference between each feature. For each instance, you sum these up, take the under root of it to get your distance. Right? So this is how you calculate the distance. This is Euclidean distance we are talking about. You can also use a Manhattan distance or the city block distance. Right. Now that brings us to normalization. When the data is collected for any data point, that data is basically derived from various sources, right? So, and the attributes or the features are calculated on a are all calculated on different scales, right? So let's say if you have 1, 2 or m features, right? These are features. So let's say x1 is a discrete feature, so it is either yes or no, right? X2 may be a real valued, but it's from yeah, it's a real valued, so it can be 999, 700, 800, or anything, right? Similarly, xm ranges between 0 and 1, so it can be 0 0.1, 0 0.5, and so on, right? So we have different types of values, right? But when we are presenting these values or these data points to our algorithm, we need to normalize it. And to normalize it, we need to scale these features with respect to each other. So what we get is minus VR upon max VR minus min VR. Okay, let's take the example for x2. Let's say the maximum value that x2 can have is 999, right? And the min value can have is 0. So in order to scale it or to normalize it, what we'll do is, let's take the value 700. We subtract the minimum 0. This would give us the normalized value for 700. We do this for all the data points and we get the normalized value for all of them, right? Now, when do we use our K-nearest neighbor algorithm, right? Or nearest neighbor algorithm? Uh, the first point would be, okay, so we should use it. Okay, when to use? We should use it when the instance can be mapped to points in R, right? If the instances can be mapped to real values or the values in R, right, we can use nearest neighbors. The other time when we can use nearest neighbors is when we have less than 20 features, right? Because when we are calculating about two features or one feature, we're just using a 2D plane. But if we have more features, we would have to use n plus 1 plane, and that would lead to uh, tougher calculation of distances and longer processing time. So it is not very efficient to use larger number of features because it increases our dimensionality. This is also called curse of dimensionality, right? Because as the features increase, our dimensions also increase, hence processing time also increases. Hence it's not very efficient. uh, we can use nearest neighbors when we have lots of data, right? The more the data, the better the accuracy of classification is. So there are few advantages to it. The advantages being it is fast, it's accurate, uh, it can easily learn complex functions, right? There's no back propagation or anything of that sort, so it can easily learn complex functions, and it does not loses info by to generalization. Basically, it keeps all instances, it uses all features, so no info is lost, no information is lost. So anything that has its own advantages will also have its disadvantages. So the disadvantage number one is curse of dimensionality. Number second is it's slow. Why is it slow? Because as I said, we need to present the whole of our training set in order to make a prediction out of it, right? The entire data is used to derive a prediction. Therefore, it's slow. Number third is problem with noisy data. If we have noisy data, nearest neighbor algorithm is not that efficient, particularly with outliers, because it is very difficult to identify noisy data. And number fourth is it's also its advantage, but it's also kind of its disadvantage, because it uses all the features to make our predictions. Some of the features might not be that useful, but still it will assign the same value or the same word to that feature, hence leading to inefficiency. Therefore, it assumes all features to be equally important, which is wrong. Assumes all features to be equally important. Right. So that completes your nearest neighbor. And that also completes your classification part 1. Done. Thank you.